All right, so inside every single one of your devices, your computer, your phone, even your gaming console, there's this incredible duo working behind the scenes. We're talking about the CPU and the GPU. You can think of them as the brain and the brawn of your machine. And today, we're going to dig into what they do, what makes them so different, and how they team up to make everything work.
But let's kick things off with a question I'm sure you've asked yourself. You've probably noticed this, right? How can your computer be a total genius, juggling a dozen different programs without breaking a sweat, but then the second you fire up a new graphically intense game, it starts to chug? Well, the answer to that mystery is all about the fundamental difference between these two processors.
So here's our game plan. First, we're going to properly meet the brain and the brawn. Then, we'll get into why one just isn't enough for modern computing, and we'll see how they're built completely differently right down to their cores. We're even going to peek into the pros playbook to see how developers unlock their true power before we see them in action as the ultimate tag team. Let's jump in.
All right, part one. It's time to get properly introduced to the two main characters in our story, the processors. So on one side, you've got the central processing unit, the CPU. And yeah, it really is the brain of the whole operation. It's this incredibly versatile, super fast generalist. The CPU is designed to crush a huge list of different tasks one after the other, in sequence, but really, really fast. You know, your operating system, your web browser, all that stuff. The CPU is the master of all those trades.
And then, on the other side, you have the graphics processing unit, the GPU. Now, this is our specialist. The GPU was basically born to do one thing and one thing only: massive parallel processing. We are talking about a piece of hardware specifically designed to handle thousands, sometimes even millions of simple calculations all at the exact same moment. It's a totally different way of thinking.
So if you take away one thing, it's this. The CPU is your flexible, do-it-all problem solver that's handling a super diverse to-do list. The GPU? That's the powerhouse, built from the ground up for huge, simultaneous jobs. Two very different but equally critical roles. Okay, so that brings up a really important question. If the CPU is this super capable brain, why isn't it enough? I mean, why do we need the GPU at all? Well, the answer has everything to do with the crazy computational challenges we face today.
This analogy just absolutely nails it. Picture the CPU as a brilliant, hyper-efficient office manager. It can handle your emails, run a monster spreadsheet, manage all your files, and it switches between all those different complex tasks so quickly it feels like it's doing them all at once.
But, here's the catch. What happens if you walk up to that brilliant manager and ask them to do something different? Like, say, calculate the exact color of 1 million tiny pixels, all for a single frame of a video. Well, their one-at-a-time approach would just completely fall apart. It would create a massive bottleneck, and they'd be totally overwhelmed. And that right there is the whole issue. So many of today's most demanding jobs. I'm talking about rendering incredible visuals for games and movies, running huge scientific simulations, and training the AI models that are changing everything. They all demand that massive parallel processing. That brilliant office manager just can't do it. You need a completely different tool for that job.
And that leads us right into the solution, which is all about architecture. It's the reason these two processors are built so fundamentally differently, right down to their very cores.
You see, CPUs are what we call latency optimized. That's a fancy way of saying they have a small number of really powerful, heavyweight cores. The entire goal here is to reduce the time, the latency it takes to finish a single complex task. For a CPU, the number one priority is get this one job done as fast as humanly possible.
GPUs, on the other hand, are throughput optimized. They are just packed with thousands of simpler, more efficient, lightweight cores. Here, the goal isn't speed on one task. It's about maximizing the total number of things, the throughput, they can do all at once. It's all about sheer volume.
So, let's just lay it all out. The CPU is like a Swiss Army knife. It's super versatile, ready for any complicated one-off job you throw at it. But the GPU, that's more like a massive team of construction workers, where every single worker is doing a simple, repetitive job, but all together, in perfect sync, they can build something enormous. One is laser-focused on low latency, the other on high throughput. Okay, so we know the GPU has all this incredible parallel power, but how do developers actually tap into it? How do they unlock that potential? Well, for that, we need to take a look inside the pros playbook. Yeah, developers don't just guess.
To really squeeze every last drop of performance out of a GPU, they use specialized platforms and follow these incredibly detailed best practice guides. A perfect example is Nvidia's CUDA platform, which has these huge manuals that are basically the keys to turning all that raw processing power into real-world speed. And one of the core strategies you'll find in there is something called the APOD cycle. It's this never-ending loop of improvement. First, you assess your application to find the slowest parts, the bottlenecks. Then, you parallelize that code so it can run across the GPU's thousands of cores. After that, you optimize it, tweaking and tuning for maximum efficiency. And finally, you deploy the new, faster version. And then, what do you think happens? You start the whole cycle over again, always hunting for more speed. But if there's one golden rule in all of this, one high-priority takeaway, it's this. You have got to minimize the data transfer between the host, that's the CPU, and the device, that's the GPU. The best way to think about it is like a bridge connecting two super-fast cities. It doesn't matter how fast things are moving in those cities, if that bridge is clogged with traffic, the whole system just grinds to a halt. Making that connection efficient is absolutely critical.
Okay, let's put it all together now and see this duo in action as the ultimate tag team. And honestly, there's no better example than looking at how video games work.
So in a game, the CPU is basically the director. It's managing the whole production. It's running the game's logic, the rules of the world. It's controlling the AI for every single character, it's calculating the physics for every explosion, and crucially, it's getting all the data ready and telling the GPU exactly what it needs to draw.
And the GPU? Well, it's the visual effects superstar. It takes all those instructions from the director and just makes the magic happen. It renders all the 3D graphics. It creates those amazing special effects like realistic fog and shadows. It wraps detailed textures around every surface, and ultimately, it's doing the billions of calculations needed to decide the final color of every single pixel on your screen over and over, dozens of times a second. So, the big takeaway here is pretty clear. This is not a competition, it's a partnership. A balanced system is everything. If you pair a monster of a CPU with a weak little GPU, or the other way around, one is just going to be sitting around waiting for the other one to catch up. And that bottleneck is what causes that horrible, choppy, stuttering performance that can totally ruin a game.
And all of this leaves us with a really fascinating question about the future. For so long, we thought of the GPU as the specialist, right? The brawn. But the very things it specializes in, AI, machine learning, those things are rapidly moving from the edges of technology right to the very center of everything we do. So, is the GPU's role about to change? Could the brawn of today actually be evolving into the new dominant brain of tomorrow's computing? Now that is something to think about.